Hi, I'm Zongshang from Osaka University. In this presentation, I will talk about our paper titled Revisiting Pixel-Level Contrastive Pre-Training on Scene Images. I will first introduce the preliminaries needed to understand my research, and then I will dive into the method section, the experiment section, and the conclusion section. I want to first introduce the concept of image-level representation learning. It is essentially about converting RGB images into numeric feature vectors, which can then be used for tasks such as image classification or object detection. In order to perform such an image-level representation learning, we can either use supervised learning when we have annotated data, or otherwise we can use self-supervised learning. We are interested in such an image-level representation learning because we can either directly apply the learned features for image classification or transfer the features to more complex tasks such as object detection, instance segmentation, or semantic segmentation. In our research, we are more interested in self-supervised learning. The key to self-supervised image-level representation learning is to pick a pretext task for training, such as image colorization or rotation prediction. We can also use contrastive learning, where we need to maximize the feature similarity between the two augmented views of the same image and minimize the feature similarity between the views from different images. Self-supervised dense representation learning, as opposed to image-level representation learning, focuses on learning spatial features rather than image-level features. The reason why we want to learn the spatial features explicitly is that although image-level learning can also give us reasonably good spatial features, they are often less discriminative for dense prediction tasks such as semantic segmentation or object detection. So how do we perform such dense representation learning in a self-supervised way? It can be categorized into two classes, pixel level and region level. Pixel-level learning tries to match individual cross-view spatial feature vectors as positive pairs for contrastive learning. Region-level learning tries to match groups of spatial features, and in order to select such groups of features, we need to rely on object priors, such as object bounding boxes or semantic segmentation masks. In this research paper, we try to revisit the assumptions that region-level learning makes about pixel-level learning. More specifically, region-level learning assumes that pixel-level learning only learns local semantic information rather than more holistic object-level semantic information. And it also assumes that pixel-level learning is subject to false matches when dealing with scene images where there are multiple objects. For example, the panda here only exists in the first view, so when we try to find the positive matches of panda feature vectors from the second view, they simply do not exist. Region-level learning can naturally mitigate this problem because they rely on the object bounding boxes or segmentation masks. In this paper, we will challenge these assumptions. Firstly, we propose a pixel-level contrastive learning framework called PixCon by combining previous good practices. In this framework, we have two models. Each model takes one of the two augmented views as input. Each model has two branches, one branch for image-level learning and another for pixel-level learning. Both image-level learning and pixel-level learning have their associated contrastive losses. We study different variants of performing pixel-level learning to challenge the assumptions made about pixel-level learning. The first variant of pixel-level learning is based on similarity-based matching to retrieve the positive pairs for contrastive learning. For example, if we want to find the positive sample of the feature vector in the first view, we need to first compute the dot products between this anchor feature vector and all the feature vectors in the second view, and pick the feature vector in the second view with the maximum feature similarity as the positive sample. After we retrieve all the positive pairs based on this similarity-based matching, we can use them for contrastive learning, where the negative samples come from the special feature vectors from other images. The second variant applies coordinate-based matching, which requires to first extract the overlapping areas of the two augmented views, and then we need to use inverse augmentation to spatially align the feature maps of the overlapping areas. After the inverse augmentation, in order to retrieve the positive pairs for contrastive learning, we can simply map the spatially corresponding features as positive pairs. Similarity-based matching can sometimes provide semantically inconsistent matches because the similarities between features might not always make sense. But it is better at relating spatially distant pixels, which is important in object detection because we want to correlate all the features coming from the same object. The coordinate-based matching is better at providing matches with better semantic consistency, but such matches only focus on local semantic information because they are basically the feature vectors from the same image patch in two different views. Therefore, we propose another variable of PixCon, which is called PixCon semantic reweighting, which will be explained in a minute. The proposition of PixCon SR is based on several observations. The first observation is that the magnitudes of feature similarities can reflect semantic relevancy. For example, if we pick a feature vector from the blue bounding box and calculate its dot products with all the feature vectors in the yellow bounding box, take the maximum value and visualize it in the heat map, we can see that the maximum matching similarities for the fire hydrant are the lowest among all the pixels in the blue bounding boxes. And this is because in the yellow bounding box, there are no objects semantically related to this fire hydrant. The second observation is that pixels in the two views' intersected areas are more likely to find good similarity-based matches across views. This is because such pixels are guaranteed to have semantically related cross-view matches. At extreme, we can match the same pixel in the two different views. In this visualization, for all the matches with pixels lying in the intersected area, we visualize 4 with the smallest matching similarities. And such matches have relatively low similarities, but still, they are semantically relevant. Based on the two observations, we propose a semantic weighting strategy. Specifically, we multiply the contrastive loss term for each positive pair with a semantic weight called W here, and capital A here is the normalization factor. For each positive pair where the anchor pixel lies in the intersected area, we set the semantic weight as the maximum, 1. For other positive pairs, we use the matching similarities as the semantic weight, but we choose to rescale it to 0 and 1 and sharpen it to achieve better performance. As can be observed from the visualization, the semantic reweighting strategy can help us exploit matches more likely to make sense and also explore more useful matches while mitigating those with low confidence. For evaluating the performance of our pixel-level learning framework, we evaluate the model on different downstream tasks, such as object detection, semantic segmentation, and instance segmentation across different datasets. Before we proceed to the quantitative results, we can review the differences between region-level learning and pixel-level learning. As can be observed in this table, we can see that pixel-level learning does not require any of these components crucial for region-level learning. As we can observe in this table, all our variants of the pixel-level learning framework can achieve competitive performance compared to the region-level learning and image-level learning. Especially for the PixCon SR variant, it achieves the best performance among all the variants, and also it can achieve SOTA performance compared to more complex region-level learning methods. We visualize the self-attention maps of the best variant of our pixel-level learning framework, PixCon SR. As we can see, even though it only applies pixel-level learning, it can still learn holistic object-level semantic information, as opposed to the assumptions that region-level learning methods made on the pixel-level learning methods. In conclusion, we proposed a pixel-level contrastive learning framework called PixCon to unify previous good practices in self-supervised visual representation learning. Then we analyzed different matching algorithms for finding pixel-level positive pairs. Then we proposed a semantic reweighting strategy to improve pixel-level learning. Thus, we challenged the assumptions that region-level learning methods make about pixel-level learning methods. Thank you for listening.